highlighted in red, and I will read those questions out after the webinar during our Q&A segment. All webinar attendees are eligible to receive one NETA CTD and one PDH or 0.1 CEU just for attending today. You will receive this in an email within about 2 business days of the webinar. And that email will also include a copy of the PowerPoint presentation and a link to the video recording of the webinar if you'd like to watch it again or share it with your colleagues. So remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Okay, our presenter today is going to be Jill Duplessis, Megger Global Technical Marketing Manager. And also to assist with the Q&A session at the end of the webinar, we'll have one panelist joining us today by the name of Diego Robolino, and he is a Megger Principal Engineer. Okay, let's go ahead and get started. Thank you for joining us today, Jill.
Thanks, Jamie, and a very warm hello to everyone listening in. I really appreciate your interest in this topic and grateful for the opportunity to talk to you today about electrical insulation diagnostics. Our specific focus, of course, is on a test that I prefer to call narrowband DFR. For today's webinar, I thought that I'd start with an introduction that briefly casts me in the role of historian as we explore how we've come to this point today where we're talking about narrowband DFR testing. Since narrowband DFR is a repetition of tests that is performed each time with everything held the same except for the frequency of the applied test voltage, we will first talk about the influence of frequency on dielectric behavior. And with this knowledge in hand, we will review some proposed analytic guidelines to interpret the narrowband DFR test results. From there, I'll share some helpful thoughts to illustrate how certain parameters, namely temperature, moisture, and oil conductivity, influence your narrowband DFR test results. And the significant advantage of DFR testing is that it allows you to determine the unique and individual temperature correction for an asset. And I'm really keen for you to understand how this works. If you walk away with one thing from this presentation, I want you to appreciate the importance of correcting your power factors to accurate, equivalent 20-degree C values, and also understand the only way in which this can be effectively done. Our last topic will be musing of sorts, where we will reflect on the predictive nature of this test as compared to online monitoring. So with that hefty agenda, let's go ahead and establish right away that narrowband DFR is just one of several tests to assess dielectric health. There's no need to pick a team here. People seem to like teams in general, something to identify with and get behind. So if you must, pick team insulation testing, on which we have several great players, each with their different strengths. And you really ought to be familiar with them all. Electrical insulation testing needs have existed as long as the electrical assets themselves. Early attempts at insulation design are really interesting to read about. For example, back in 1880, when Thomas Edison, who's pictured on the upper right-hand corner picture in the car there, well, when he installed his first lighting system in New York, he thought that wood was a good insulator and predicted that because the voltage was low, there wouldn't be a problem with any leakage. So they settled on the design, they dug these shallow trenches, they laid wooden moldings in them, and placed the wires in the grooves. Then Edison decided, hey, I'm going to wait for a wet day to conduct a full-scale test. Rains came, and electricity went in all directions, and even the trees were charged. So next he tried pouring coals into the grooves. That failed. He wrapped muslin around the wires, failed. And ultimately, after better respect for the importance of insulation, and some thorough investigation, he discovered that dipping the muslin in a compound of asphalt mixed with linseed oil and small amounts of paraffin and beeswax would do the job. So insulation testing, I would say, might have very much begun as a functional check. You know, does it work or does it not? But it didn't take long for the foremost need of testing to be the assurance of safety. And insulation systems obviously have evolved significantly since those days. And I would add to this now the longevity of the asset as another considerable reason for testing insulation. But then now the need to test insulation never goes away because the consequences of failure are too high. Earliest tests on insulation systems involved applying a DC voltage across the insulation and measuring the leakage or the resistive current through it. And the first DC portable insulation tester was developed in 1889 by our founders, Sidney Evershed and Ernest Vignoli. And by 1903, it was being sold as a mega insulation tester. Then, within the following decade or so, a cleverly constructed device came along that revealed unmet testing needs. So what's this device? It's a condenser bushing, or more commonly known as a capacitance-graded bushing. And manufacturing problems with these type bushings were not being consistently identified using DC insulation resistance methods. So manufacturers turned to power factor and capacitance tests as an alternative. Because of its construction, a capacitance-graded bushing is actually the perfect test specimen for a power factor and capacitance test. The entire insulation system, kind of pictured here on the right, is a compilation of miniature insulation systems. The manufacturer can achieve this design by embedding conductive inserts spaced evenly throughout the bulk insulation material. The purpose of these individual conductive layers are to control the voltage distribution across the bushing so that it's held evenly across each layer. So this means that should one of those layers deteriorate with a steady voltage held present, losses will be significant across that layer, and then the average layer condition will reveal the localized problem. And that's what power factor is all about, is reporting back the average condition. Capacitance, meanwhile, stays constant in that kind of case, but once a layer ultimately fails in short circuit, capacitance increases from its benchmark. And because of its success with bushings, it didn't stop there. So everything was being power factor tested, and the lofty expectations from the test didn't change. So how has that worked out? Well, we're still doing it, but have we been stuck in a so-called waiting place? There are many deficiencies associated with a power factor test to suggest that this may be the case. So I'm going to pause for a moment to say that I rather expect that all of you have familiarity with power factor and capacitance testing, but nonetheless, I'm going to take a few slides to anchor what we know about the test. And of course, the purpose of electrical insulation is to store electrical energy when surrounded by an electrostatic field. This is exactly what a capacitor does. So one way to assess how well insulation is behaving is to model the asset with capacitors and then trend the corresponding measured capacitance values with time. This is definitely a functional assessment. Is electrical charge holding capacity of the material still the same today as it was on day one? But there's also certain health information provided this way too. If you look at the equation for capacitance here that I've shown, it's the dielectric constant of the insulating material, epsilon r, times the geometric capacitance, epsilon naught times area of the plates, in this case, electrodes, divided by the distance between them. And of course, the components of the geometric capacitance are physical in nature, area and distance. So a change in capacitance indicates either a geometric change with the system or possibly significant changes to the composition of the electrical insulation materials that in turn influence epsilon R value. In a power factor or dissipation factor test, I'm going to use those interchangeably, the test instrument applies an AC test voltage at 50 or 60 hertz and measures the total current through the insulation. And then the test instrument resolves this into capacitive and resistive components. And from there, calculations of the other reported electrical characteristics that we're used to seeing in this test, including capacitance that we just talked about, those calculations are made by the software. So capacitive current is representing energy stored by the insulating materials. Losses are related to the real current or resistive current flow. And what we're interested in is the phase angle relationship of that total current to the applied test voltage, because that phase angle hints at how much loss current we have present in the measurement. And as that loss current or resistive current goes to zero, then our power factor will be zero, indicating, and generally indicating that the insulation system is in good health. And as the insulation ages or becomes contaminated, that resistive current increases and power factor will often follow suit and increase as well. So the reason we don't settle on looking at reported losses themselves is because those are influenced by the size of a specimen. The larger the specimen gets in the same condition, still the more losses that are going to result. So power factor takes the size into consideration and reports the system's relative losses. Out of the total electric field that the insulation is subjected to, what percentage is lost to heat, and AKA is unrecoverable. Now, as far as assessment of power factor, it's all about comparison, comparing to benchmark values, to previous values, which are actually the same as benchmark values, but previous test results. And as a last resort, if you've got nothing else, comparison to limits. Obviously, trending is a preferred analytic method, but it requires more than one previous result to create a trend. To give some perspective about expected power factor results in insulation testing, we'll take a look at limits established for transformers and also some of the associated analytic guidelines. The primary insulating dielectrics in the transformer are mineral oil and mineral oil impregnated paper. That for normal in-service and in new power factors for mineral oil filled transformers, limits are dependent upon the voltage rating of the transformer. If it's less than 230 kV, it's 0.5% once it's been corrected to a 20 degrees C reference. For greater than or equal to 230 kV, that's tightened up a bit, and the ultimate power factor limit for acceptability would be 0.4%. Now, as far as the power factor limit for continued serviceability, can I keep this transformer in service or not? That's 1% at 20 degrees C. Any power factor results you measure between 0.5% and 1% are generally looked upon as, hey, this requires some additional testing and investigation. So I want to move on to the deficiencies of power factor, and that's what's summarized on this slide. So averaging, that's a double-edged sword. Ultimately, it is the key to power factor success. Averaging is why it works in certain scenarios like bushing testing when the insulation resistance doesn't work. Namely, it's why you can see a localized problem. But averaging is definitely not perfect. It requires the asset to be small. Otherwise, the averaging effect may make it harder to see a problem. And then when you have signs of deteriorating health, it's hard to discriminate between a localized problem and general deterioration. So these cartoon images I'm showing here on the right, holding up test results, the average in both of these cartoon images are 90, so less than a perfect 100. But from that value, from that average, you can't determine which scenario you have, the case on the left or the case on the right, where everybody scores 100 but one student, or everybody scores the same exact value, it's just less than perfect. Another problem with power factor tests is that they are not acutely sensitive to many problems at line frequency. And when a problem is indicated, it's also impossible to differentiate and characterize the source, leaving why has my power factor changed unanswered, and you're left with many questions. So I'd like to put into perspective this not acutely sensitive to problems at line frequency with this next slide. On the y-axis of this figure, we have dissipation factor plotted at, dissipation factor measured at 50 hertz plotted on a logarithmic scale. And then on the x-axis, we have the percent moisture in cellulose. And we're looking at two curves here. The one in blue is a dissipation factor plotted for a new transformer, and the one in red is a dissipation factor plotted for a service age transformer as each one becomes increasingly contaminated with moisture. So what can we see from this figure? Well, first, the slopes of both responses are relatively flat at low moisture levels. Oops, I don't know what I just did. Sorry about that. At low levels. And in this region, you can see that dissipation factor doesn't increase noticeably as moisture is increasing. So somebody that's relying on a line frequency power factor measurement as an indicator of moisture will be unaware that moisture contamination is present and that it's trending upwards. It's not until the moisture in paper is probably at least, I don't know, 2.5% that the slopes marginally increase, and maybe 3.5% when the slopes notably increase, at which point it could be said that dissipation factor then has a heightened sensitivity to moisture when that slope really goes steep. So in spite of its eventual sensitivity to moisture that seems to occur around that 3% mark, dissipation factor, even at that point, is still only 0.5% if you look at this orange dotted line. So moisture content, almost 3%, power factor around 0.5%. And of course, we just reviewed the limits for power factor, so that's probably not going to flag such a big concern. And just for perspective, operators usually become weary when percent water content exceeds maybe 1.7% moisture in cellulose, and by, I don't know, maybe 2.5% are typically scheduling a processing unit to dry the transformer. And so one more thing I want to note about this graph is that the divergence or separation of the two curves at the low moisture levels. This indicates that a single dissipation factor may represent a wide range of moisture contamination levels, and it's largely dependent then on how aged the insulation system is. Like, for example, if we take the green dot at 0.3% dissipation factor, that's obtained for moisture content ranging from 0.5% in the case, if you see that first vertical green dotted line, so that's in the case of a service age transformer, to up to 2% if you're testing a new transformer. So this presents a challenge since it's not straightforward task to quantify the aging of a transformer. You can't go on years in service to quantify the aging of a transformer. It's just simply not reliable because environmental and system variables, maintenance, other factors all have a role in how the insulation is going to age. So in summary, this lack of sensitivity to some problems at 60 hertz means that if you start to get some small changes in power factor, they could be significant. And that's why trending of power factor is the best analytic tool. But the challenge becomes filtering other variables that may be influencing your test results, for example, like temperature, so that the trending that you're reacting to is meaningful. Okay, so it turns out that narrowband DFR testing, where we examine the power factor as a function of the test voltage frequency, holds a key for improving a power factor test potential for success. So let's turn and examine the influence that frequency has on insulation behavior. Before I do that, though, I want to mention that several diagnostic techniques are based on frequency, and those include SFRA, which is sweep frequency response analysis, of course, dielectric frequency response DFR, and narrowband DFR, which we are talking about here today, and FRSL, or frequency responsive stray losses. Each of these tests is unique, so it's important that you understand the differences between them. SFRA is probably the most widely known test of the four. It's used to check the mechanical integrity of a transformer. And in this test, a low voltage signal is injected into one end of a winding, and it's measured at the other end of the winding so that the electrical transfer function can be determined. Or in other words, we're looking at the transformer's behavior as a complex impedance. And this, the impedance that it represents to or presents to the circuit is dependent on the frequency of the signal you're putting through the winding. So we repeat the test many times over a range of frequencies from 20 hertz to 2 megahertz. And I just want to pause and say right here that if you're interested in truly understanding SFRA testing, we are planning, or we are publishing a highly informative 4-part series on SFRA this fall that takes an in-depth look at this diagnostic. And this is going to become part of Megger's Transformer Life Management Bulletin series. So if you've been missing out on these, I've included the link in this presentation for you to check out this free and educational resource. In a DFR and narrowband DFR test, we are looking at the relative losses of the insulation as the frequency of the applied test voltage changes. So we're also looking at something with a change in frequency, but it's different than the something we're looking at in SFRA. Yeah, so relative losses of insulation that we're interested in. So in other words, what percentage of the total electric field is lost at heat at each frequency? And finally, the FRSL test looks at the behavior of the resistive part of short circuit impedance measurements as the frequency changes. So as I've said, okay, we're going to look at the full DFR test. We're plotting insulation losses relative to the total energy present as a function of test voltage frequency. We're really interested in how the electrical characteristics of our insulation is changing as we subject it to test voltage signals that are really slowing down or that are getting faster, faster, faster. And the results, which I'll show on the next slide, are displayed as a curve. With these results in hand, an insulation model is used to recreate that measured curve as closely as possible by adjusting parameters of the model. And once a model curve is fitted, then we have in hand the moisture content of the cellulose insulation that we just tested and the conductivity of the oil. This test takes just under 20 minutes to measure up to 2 insulation components at a time, say CHL and CH. Goes faster if your insulation system is in worse condition. And then this last bullet point, I'll say that later in the presentation, I'll be making mention of temperature as a diagnostic means to assess insulation health. And so at that point, I'll be referring back to this last bullet, essentially saying that from your DFR test results, Megger can convert the results to a power factor versus temperature plot, or dissipation factor as a function of temperature. Okay, so here's a representative DFR curve. We're plotting power factor, or actually in this case, if you look at the y-axis label, we're plotting dissipation factor with frequency. Gosh, otherwise you might be thinking, I wish I could get, here we go. Otherwise you might be thinking at this lowest frequency and low. How did my power factor here go over 100%? Right, and that's pretty impossible, but not with dissipation factor. But still, you can immediately see that electrical losses in the insulation become really high when we go down in frequency. Remember that power factor is reporting what percentage of the electrical field present is lost as heat. So when you're up at 100%, everything's being lost, nothing's being stored, so it's unrecoverable. But thank goodness that we're operating electrical equipment at 50 or 60 hertz over here, or we'd be having a Thomas Edison deja vu. Okay, so obviously we came together today to talk about variable frequency power factor, but I'd say that the general preference and consensus is, hey, let's call this narrowband DFR testing, because after all, it's a subset of the full DFR measurements. Also, the name narrowband DFR solves this problem of whether we should be naming this testing power factor or dissipation factor, right? I mean, it's always like, what do you call it? But Yeah, we'll just take them both and out of the picture and call it narrowband DFR. These measurements are done from 500 hertz down to 1 hertz. The narrowband DFR testing consumes a lot less time than a full DFR test. It takes just over maybe 2 minutes per installation component, and we are performing the test with our dedicated power factor test instrument, not a separate instrument. But by foregoing a true DFR instrument, we lose modeling capabilities in the database. So we won't be getting moisture estimations or oil conductivity intelligence. So I guess that leaves us with a question, then what are we getting? So let's just continue on here and find out. So this is a sample narrowband DFR test result that we will be revisiting when we talk about analyzing narrowband DFR results. Which you can see it's just a smaller subset of the graph I showed you 2 slides back for a full DFR measurement. But before we get to the analysis, we need to arm ourselves with some additional understanding. We're interested in learning more about the influence of frequency on the electrical characteristics of insulating materials. We've already seen that power factor is going to change quite widely as the frequency of our test voltage changes. So let's explore this. More. And actually, a good place to start is by looking at what happens when we apply DC voltage to an insulation in the time domain. And this is a nice figure here and comes right out of Megger's classic, A Stitch in Time, first edition of which was published all the way back in 1966. And just some general observations from this graph here. So here, total current measured is shown as a function of time. Time is on the x-axis, and amps are shown on the y-axis. And so you can see that it's broken further into its components. By the way, I can assure you that, I'm trying to get this mouse to show up. Sorry about this. Here we go. Okay, so I can assure you that the total current extends further to the left, but it's just not shown on this particular graph. This is an empirical graph, but I still like it. And for that matter, beneath that, beneath the total current is my absorption current, and the same thing. It's not fully shown either, but it still exists starting at time 0. But taking further note of the axes and the scale, you can see that we're plotting very small currents here. So on the y-axis, we're showing just up to 0.1 milliamps, and then at the lower end of the range is 1, at the very bottom left-hand corner is just 1 microamp. So we're dealing with some really small currents that are being plotted here. We're also not revealing on this graph what happens less than 0.1 seconds. So from 0 to 0.1 seconds, we're not showing. The graph starts, the x-axis starts at 0.1 seconds and then continues up to 10 seconds after application of the DC voltage. Total current through the insulation is time dependent, as you can see, and of course it's equal to the sum of all currents present at the instant of its measurement. So in fact, the plan is to next talk about each of these 3 subcomponents of the total current separately. But to kind of explain some of it right now, essentially we're measuring current that is representing the energy being stored by the insulation. That would be the capacitive charging current, and current associated with the energy that is dissipated as heat. And this aptly named loss current has 2 subcomponents. So there's the conduction current or leakage current that's shown here, and absorption current, which is also sometimes called and probably better known as polarization current. We should note the time constant associated with the conduction current through the insulation. It doesn't happen immediately, it builds up. And if we let enough time passes, so if you can imagine going off the right of this graph, the total current is eventually going to diminish to conduction current only. And as a final observation here, just keep in mind that, the lower the magnitudes of this current represented on the graph would indicate the better health of the insulation. It would infer that the insulation resistance is quite high of the material, and therefore just very little conduction current can flow. Okay, so just a further comment about the capacitive charging current in the time domain. We just saw that it was real, that it was plotted. But if you look at the equation for capacitive current, which is equal to capacitance times the time variation of the voltage field, you can see that, or you can then figure out that, hey, DC, I have no variation in my voltage, so that should tell me that my capacitor doesn't pass DC current, and that is true. However, the voltage across a capacitor doesn't change instantaneously. There's time required for the electric charge to build up on the capacitor plate. And the dielectric, the material separating those electrodes, the size of the electrode, and the distance between those electrodes are going to enhance this effect. So capacitive current is really asset specific. I can't just draw one graph with a representative capacitive current for that covers all insulation systems. That's absolutely going to vary. Okay, so now let's consider what happens in the case of a time-varying electric field. So on this slide, I'm showing representations of two arbitrary signals, an 80 hertz signal in gray and a 10 hertz one in orange. So obviously the gray is gray. Okay, sorry for that interruption there. But I was saying that obviously the signal in gray is about 8 times as fast, or precisely 8 times as fast as the one in orange. So when we apply an AC voltage to our insulation, the same physical effects we just observed when a DC voltage is applied, the same effects are at play. But the frequency of the signal becomes a big deal to determine what is happening with our measurement. The electrical characteristics of the insulation are highly dependent on how long that voltage is applied in one direction before we reverse the polarity of the applied voltage. So going back to this graph, the frequency of the applied test voltage is going to determine how far we get on the graph from time 0 before the polarity of the applied test voltage changes. So you know, of course, that the period of a sine wave is equal to the inverse of time. So on the left side, sorry, I'm still trying to get my mouse to pop up here. But on the left-hand side, as you go down further into lower amounts of time, that's going to be associated with higher frequencies. The polarity of the field is varying quickly, so not much time passes after application of a voltage before then we reverse the polarity and everything changes. Whereas on our lower frequencies, those are associated with a lot of time passing before we change the polarity of our voltage and things change. So more of these effects can start to play out before we then reverse the polarity and change things again. So I guess I would want you to take note on this graph of the changing relative proportions of the capacitive current to conduction current. So at these higher frequencies, and you can imagine as we're getting to 60 hertz, and I would tell you this capacitive charging current, goes quite large. I mean, if you think about transformers maybe and some of the capacitive currents that you might see, I mean, you might be dealing with something like 40 milliamps or something like this, not 0.1 milliamps. So that's gonna go quite large. Whereas the conduction or leakage current is really just a small portion of that total current that you're going to measure relative to the capacitive charging current. But as more time passes, and that's what you see with the lower and lower frequencies that go so slowly before they change polarity, conduction becomes then a big dominating factor in the measurement, and capacitive charging current eventually goes away. The plates of the capacitor get charged, so the winding and the grounded, it's reached full charge. that voltage application is still steady there. We haven't reversed the polarity yet. So once it's charged, that disappears from the measurement, and then, yeah, conduction current is dominating. So here is a plot of power factor against frequency given increasing levels of conductive loss in the measurement. So if you have virtually no conductive loss, then you're pretty much on the floor of the graph at nearly all frequencies. But with a small amount of conductive loss present, it's pretty clear that conductive loss is easier to see at these lower frequencies. And that's what we just described on the previous. So in that situation then, at these lower frequencies, changes in conductive loss from a benchmark value when the insulation was in known good condition becomes much easier to see. So if you're dealing with insulation systems that are very large, where under normal situations at 60 hertz measuring, the conductive loss current is extremely tiny compared to this relatively huge capacitive current. Testing at lower frequencies is going to give you a better ability to detect that loss and see if something's happening that's in the insulation that's causing a change in conductive loss from previous, and that's a valuable feature of going down to these lower frequencies. Next, I want to talk about that absorption current, and I told you that it's synonymous with the polarization current. And so basically, this is associated with polarization processes that happen in insulating material when you apply voltage to them. There's several types of electric polarization. I've listed 5 families that are shown here from fastest occurring to slowest. So you've got electronic that happens immediately, then ionic polarization, orientational polarization, hopping polarization, and interfacial polarization. The first group of the 3 polarization processes are due to fixed charges within the material. So just to give you an example of how this is working and how polarization processes contribute to losses measured in insulation, let's consider the electronic polarization. This is the fastest occurring of the processes happening immediately upon application of the field, and we're talking probably in the microwave frequencies. And this is when the electron cloud or ring around the nucleus of an atom will actually, the cloud shifts with respect to that stationary atom. So it's not movement of the entire atom, it's just movement of that electron cloud. Well, when it tries to move, there's inertia that's opposing the movement, and that's what results in loss. It takes for those electron clouds to displace. In the case of ionic polarization, for this to occur, first of all, the atom that we're showing here, it has to be an ion. So hence the name ionic polarization. So that means that the atom carries a positive or negative charge, that there's not balance between the electrons in the outer ring and the protons in the nucleus. So for example, elements are atoms that prefer to have a full outer shell, so they'll gain or lose electrons in order to arrive and stay at this preferred state. But when you have an ion and you subject it to an electric field, the field causes the ions in a polyatomic molecule to displace relative to each other. So it's movement of the ion, but it's movement relative to otherwise stationary other atoms within this polyatomic molecule, or I guess they'd be ions too, but they would be moving not in concert. And so this, of course, has inertia opposing this movement as well and requires work. And then lastly, orientational is where you have a permanent dipole, and on application of the field, the electric field, they want to rotate and align in the direction of the applied field, and that rotational movement is, again, opposed by inertia, so work has to take place in order for that movement to occur. Kinds of examples of polarization losses that you measure when you apply voltage to material. This next category of 2 polarization processes are due to moving or trapped charge within the insulating material. Includes hopping polarization, which is created by localized charges that may be able to move freely for a short amount of time, but then they would get trapped somewhere, and they spend most of their time in a localized state. Maybe, depending on the application of the field, maybe it develops the ability to hop and move to another state, but yeah, that's highly dependent. Interfacial polarization is produced by mobile charges that actually form positive and negative space charges at the interfaces between different materials. So in this example, it's showing volume of oil and some pressboard materials. And so with application of that field, you can see that the positive charge, moving charge particles in the oil are going to be attracted towards the pressboard, while the negative charge in the pressboard is going to be attracted towards the oil. And so they meet and form a barrier actually at that interface, and it can cause any current that would otherwise flow through this material to take a different path on how it would flow through. And typically you're seeing interfacial polarization losses at frequencies that are less than 10 hertz. So this is probably getting more, I'd say hopping polarization and interfacial polarization, these slower polarization processes are ones that you can see some influence on testing we're doing on insulation. The frequency ranges that we're considering, these would be right in there. So this next slide is showing that polarization process in place, and you can see here that it's timed so that it just finishes the polarization process. So say, for example, that, because it's easy, that electronic polarization. So the electronic cloud moves relative to its nucleus, and it just gets to its end point of where it's moving to when the field reverses, and then it goes in the opposite direction, just gets there when the field reverses. Well, this would be known as that process's resonance frequency. And so that is the frequency at which the contribution to loss for that particular polarization process would be the highest. If on the other hand, I slowed down the frequency of my voltage signal, that same polarization process would finish, and then after that point that it finishes, then it contributes no further to the total loss, because it's already gotten to where it wants to go, and it's going to stay in that position until the polarity of the voltage changes. So at really low frequencies, all the polarization processes that might happen in the material ultimately are going to finish. They're going to, the movement in the material on an atomic level and molecule level, all of that movement and charge movement will ultimately finish if you wait long enough. And so at that point, the dominant contributor to loss is going to diminish down and be representative just of conduction current, whatever leakage current is getting through that material. On the other hand, if I was to really increase the speed of my test voltage signal, and this really varied really fast, far faster than the previous slide I showed you, the voltage field might reverse direction before the polarization process can hardly even begin. So the frequency of the voltage signal will really influence the amount of polarization processes and losses that you have contributing to the overall losses that you measure. And with that, that's probably sufficient background to move on now and take a look at some narrowband DFR test results. So first, let me comment that the analysis of narrowband DFR is done by visual inspection. And so always when the analysis is by visual inspection, you have to be vigilant about how you are displaying the data. Like I've got for an upper limit 4.5% power factor on these two graphs. If I was to change that to 20%, obviously it's going to be a tiny blip on the screen. And then the other comment I would make would then be about the scale, and that's shown, by the way, in a linear scale. But on the x-axis, I've shown it both in the linear scale on the left and a logarithmic scale on the right. And I would say that if your frequency range isn't very broad, you can probably, get away with the linear display, x-axis being on a linear display, because you're not trying to look at detail at some lower valuable frequencies. But as soon as you go, say, for sure below 10 hertz, then the logarithmic scale of the x-axis is really essential so that you can see all this valuable information that's held at these lower frequencies. It's the same data, but you want to make sure that your interpretation capabilities are maximized. So the preferred way to show this data is on a logarithmic scale. Now, as far as assessment guidelines, so for a transformer course, just like you have always done with power factor testing, for a two-winding transformer, as an example, you measure a narrowband DFR test for CH components, CHL components, and CL, and generate 3 separate curves. And then from there, what you want to do first thing is actually you want to assess that temperature-corrected line frequency power factor. So 60 hertz in the case of states, we want to take a look at that power factor, verify that it's corrected to a representative 20 degrees C equivalent value, and assess it on basic guidelines that we know, preferably with previous test results, and short of that against the limits. Then we want to assess the slope of the curve through 60 hertz, and a positive slope of the narrowband response, DFR response, is going to indicate healthy insulation. Another thing you want to look for is, ideally, you won't see it in all cases, but is what's called the trough on the curve, or the minimum point, kind of where it starts reversing direction from going maybe from a negative slope of the response, and I'll show this to you in a moment, to either flat or to a positive end. But where is that trough? Because, and ideally that's going to occur at a frequency lower than 60 hertz, and it's going to be a function really of how far you're measuring down to, whether you see that or not. But that's going to give you some assessment value too, and predictive value of what's happening with this particular inflation component. From there, we look at what I call the tail of the response, and so that's the higher frequencies. I'm talking higher than 60 hertz up towards like 500 hertz. Assess that tail, and the expectation is that tail is going to start to increase with frequency, but we want to keep our eye on how much it increases at these higher frequencies. And I'll give you some visual as the best way to convey that message of what's an acceptable increase in the tail or not. And then if we have the 1 hertz data available to us, we certainly want to note the behavior of the response at 1 hertz. And this really becomes beneficial too for larger specimens, which will better benefit from that better scrutiny that we get at those lower of conductive losses that we get at those lower frequencies. And previous tests really are ideal because it would tell me that, gosh, yeah, I can see I can have conductive losses, but how does this compare maybe to what it was in a known good condition? So if you have the previous available, then that would definitely aid you in your analysis. So just as an example, let's take this narrowband DFR data, and we're looking at the percent power factor of CH, let's see, in blue, CHL in orange, and CL in gray, plotted as a function of test voltage frequency. So first, again, following the previous slide guidelines, we identify the line frequency power factor in each of these. It seems like it ranges from about 0.3% to 0.35% for the 3 components. We need to, don't forget, to double check the oil temperature at the time of test to make sure that these results have been compensated for temperature back to its 20 degrees C equivalent base. From there, and I would comment that 0.3 to 0.35%, assuming that this is 20 degrees C equivalent data, that's reasonable. So the next step is let's verify if in fact that's representing good inflation systems. So we identify the slope of the response through that 60 hertz point, and each of the 3 are positive, which signals an acceptable condition. If we go further with the analysis, we want to look for the trough of the response at min point. Well, this is a case where we really can't see it because we haven't gone far enough down in frequency to identify that. And then lastly, we're going to look at the tail looking for an out-of-place noticeable increase in power factor. And these all have a gentle rising power factor with frequency, just like we expect. So everything looks good here, too. And we don't have previous tests to compare to, so that would be the kind of final step here. So here's some additional overall transformer narrowband DFR data. Power factor at 60 hertz is about, let's see, 0.22% for C and 0.31% for CH green and 0.4% for CH in blue. We had to verify on a test. And unfortunately, this is unavailable because not having represented 20 degrees C narrowband DFR data could totally screw up our conclusions that we come up with. We'll be talking about how to correct how to determine what the correction factor should be for these curves as a next topic. But I will give you a preview and tell you that it actually causes I'm trying to get my mouse back. Sorry about that. I'm not sure why it's acting so fussy. There it is. It'll actually cause general shifting. Say we were testing right now at 40 degrees Celsius when these measurements were done. Well, if we correct it back to 20 degrees C, you'll see a general shift of all these curves towards lower frequencies. And so if of course, I'm looking at the 60 hertz frequency and the slope of the line through this frequency here. But if my cursor shifted and these now became the 60 hertz points, or these, sorry about that, or these became the 60 hertz points, then you can see that perhaps the slope isn't negative after all anymore, it's actually positive. And so that's why the temperature piece becomes so critical in the analysis of narrowband DFR test results. But in this case, if we assume that this was 28 degrees C representative data, then we can observe that the slope of the CHL curve is pretty flat here, while the slope of the response for CL and for CH are negative. The flat response of CHL marks it as one to keep an eye on, while the negative slopes of CH and CL would suggest that, hey, you need to do some additional testing to see what's going on here. Maybe you have a look at the high voltage and low voltage bushings respectively, because they may be contributing to these results. Do you have some previous narrowband DFR test data to compare to? In these cases, it would be nice to have data down to 1 hertz so you could see a little bit bigger picture here, and that may provide some additional insights as well. I want to mention that even when power factor, dissipation factor test results are the same for similar assets, this can't be trusted as a reliable indicator that the assets are in similar conditions. So this graph on the left-hand side is a full DFR measurement of 3 transformers, and you can see in this case at 50 hertz, this is some tan delta measurements on transformers with operating temperatures of 50 hertz. You can see that they all have identical line frequency power factor values. So okay, we're at 0.5%. It's probably not going to be a good end to my story because it's pushing that upper level of power factor. But the point is here that, here you've got 3 transformers that are in quite different condition. So you really are limited with the knowledge that you have by just looking at the line frequency power factor. And here's another example of 2 sister transformers that were tested. This was the interwinding insulation component. They both measured around 0.4% at line frequency. And then when the narrowband DFR tests were revealed, you could see that, gosh, they look nothing alike. And given the guidelines we just reviewed, you can see that unit A here in blue is negative slope to that power factor line frequency, while unit B is looking good with a positive slope to that value. And when then the full DFR measurements were performed on it, it in fact did reveal that unit A was contaminated with 3.4% moisture content, while unit B was relatively dry with 1% moisture content in paper. So just a caution about relying on power factor alone. With bushings, very similar to transformers. However, with the bushings, we're typically afforded the convenience of testing at least 3 similar bushings at a time. So the response should be similar for the 3. Otherwise, I would say the analysis is quite similar. We're not really looking for a trough anymore on the bushings, but we are assessing the slope of the curve through 60 hertz, and we're looking at the tail of the bushing results. There's a lot of good value to be had on bushing results down at 1 hertz. And just like with transformers, if you have previous, for sure, use that as well. With bushings, you have to be careful with surface leakage. That's true of any asset that has a large surface area relative to its overall size. So you need to be sensitive to that, including humidity. But there's ways to cope with surface leakage, including cleaning, drying it, and using some guard circuits. But here we've got some data for 4 low voltage bushings. The slide on the right is actually that data after it has been temperature corrected. So you can see, compared to the graph on the left-hand side, there's been a general shift of the whole frequency curves over to the left direction. But even in spite of this, if we look at 60 degrees hertz, you can see clear negative slope through that frequency point, which is not a good sign. But the really interesting information is how at these lower frequencies, where you can pretty readily see the clear separation of X3 as compared to the other low voltage bushings. So that needs to be investigated. I have also for you an example that I showed in a presentation actually a couple of years ago in one of these mega webinars series, and this is test data from bushings at a cogeneration plant. So these were 230 kVBO plus feet bushings, and you can see the narrowband DFR results here, where clearly H3 bushing is showing a just really, really bizarre behavior with its tail. This is what I talk about, there's no longer a gentle increase in power factor with frequency. It's quite a noticeable increase in power factor with frequency. So in this case, it turned out to be loose top terminal on the bushing. And you can see a really zoomed in picture here on the left-hand side, where there's actually some discoloration at the terminal. This is the top cover of, the site glass would be underneath this, but this is the top cover of the bushing bolted down, and you can see where that discoloration takes place. So interestingly, when they tightened this terminal up properly, the bushing tested perfectly afterwards, but the decision was made to replace it anyway. And so after the bushing was replaced, they repeated these narrowband DFR test results. And you can see that bushings H2 and H3, remembering H3 was the one that was replaced here in blue, those look quite nice with the narrowband DFR results. But if anything, H1 has a positive slope through 60 hertz, but you can see that the tail of this is actually starting to cross over the other 2 bushings, which leads you to wonder that, there might have been a general installation issue going on when these were ever installed, with how tight these terminals were tightened up here, and that H1 may have been well served by having just a quick look. It's nothing as nearly as bad as what we saw with the H3, but that probably requires some attention too. Okay, so just mindful of the time, these next slides are actually really quick, and are helpful to show how certain parameters, namely temperature, moisture, and oil conductivity, will influence your test results. So we'll start, and in each of these, I'm showing, I'm just varying out of the three variables, I'm just varying one. So in this case, oil conductivity is variable, while temperature is held for each of the specimens tested at 20 degrees C, and each had a moisture concentration of 1%. So with oil conductivity varying, you can see it, when you start getting at these lower frequencies, that's where oil conductivity really starts to influence the results. And of course, this one on the top has the highest level of oil conductivity of the batch. The next, on this one, the variable or the component that's being varied is the moisture concentration. So now the oil conductivity is good in all cases. Temperature is the same, but moisture concentration is what is varying. And so you can see the influence then in a controlled environment that moisture would have on your narrowband DFR test results here. This next one is looking at, okay, what happens now? We've varied moisture, we've varied oil conductivity. What happens when we hold moisture concentration the same? And we're going to assume that this is a transformer in dry condition. Oil conductivity is going to be average and vary the temperature. And you can see that, here are the influences of temperature. By increasing our temperature, as you see on this top curve, it causes separation from the same insulation system in the same condition, only tested at lower temperatures. And keep this one in mind, because as I show you the next slide, I want to show you on the next slide what happens on a transformer that's wet, but otherwise in the same condition, tested at multiple temperatures. And you can see that this looks quite different than, and the effect is even greater on this one than compared to the last family of curves. So I would say that for this one, unfortunately, when we're testing a transformer to assess its condition, we don't really know otherwise if it's healthy, wet, dry. So accounting for temperature effects, you can already see, are not easily done. But a realistic test scenario would be one in which we don't have the ability to do these controlled studies and hold all the variables constant except for one. So all of them will be in a state of flux. So depending on your temperature and your moisture concentration and your oil conductivity can influence how these curves are looking. So this is all just, those slides I showed you are just a perfect segue to our next topic and what I really want to share with you, and that's dealing with how do we go about dealing with non-20 degrees C asset temperatures. So Megger's individual temperature correction is one of the huge benefits of performing narrowband DFR testing. We've already talked about the importance of temperature correction. We, discussed the fact that the analysis of power factor always involves comparison, and that trending is the most effective analytic method because small changes can indicate, something really bad happening, so that any change in your line frequency power factor warrants attention. But we have to eliminate the fact that, hey, our variation in test temperature can cause that change. So we don't want to be reacting to a trend that's due solely because of temperature variation. So we shouldn't be directly comparing line frequency power factor results or any power factor results made at different temperatures unless all have been corrected to a 20 degrees C reference value. Well, the challenge with temperature corrections is that the curves that we've traditionally used to correct for temperature can introduce error, giving us the wrong 20 degrees C equivalent power factor result. And the standards now caution about this. This comes right out of IEEE standards C57-1290, in which it says, hey, be careful because temperature is a real deal, and we can't account for variation in power factor using a single correction curve. So this, these two figures really reinforce that message. Here we have families of DFR responses measured at different temperatures for both a dry transformer on the left and a wet transformer on the right. So if you look, if I can get my mouse to work, we'll go over to the 60 or about 60 hertz power factor measured at 35 degrees C, which is this green curve. Now I lost my mouse again. Sorry about this. Now, if you can see that if I want to correct this to a 20 degree C base, for this 1% moisture contamination, that's not much of a correction right around here from green to red curve. But if I look at my wet one at 60 degrees Hertz, and I want to correct to 20 degrees C equivalent temperature, if I use the same correction factor to correct this from here to here as I did the 1% moisture, you can see I'm going to have error on one of the two. But what I do observe from these family of curves in either case is that the shape of the response doesn't change drastically with temperature. So no matter if I'm at 5C, 20C, 35, 50, the shape is preserved in each of these. The response just shifts with respect to frequency, but largely it remains intact. And this is not only for the 1% case, but this is also for very wet transformer. You can see that the shape is largely held intact of the response, and it's just shifting with respect to frequency. And this is what allows us to come up with what's called an individual temperature correction. So this ITC is patented by Megger in order to correct to correct to a 20 degree C equivalent value. We basically employ the Arrhenius equation. And so this equation is going to produce what's called the frequency shift factor, which is dependent on the temperature difference between the temperature I'm measuring at, so 35 degrees C, and the reference temperature I want it to be, which is, of course, 20 degrees C. So here's the here's the equation for you. Basically, it's just the e to the negative activation energy times the difference in the inverses of the two absolute temperatures being considered divided by the Boltzmann constant. You can plug your temperatures in and the Boltzmann constant and the activation energy and come up with this frequency shift factor, but you have to pay attention to the units when you do this. So I want to show you how this works. So assume we're going to test at 35 degrees C on this green curve. And of course, I don't know this family of curves. I mean, I don't have this information. I've just gone out. My top level temperature of my transformer is 35 C, and I need to test right now. I can't wait for it to cool off. So I am left with this measurement in green here. And what I want to know is, well, gosh, what would this 60 hertz power factor, which is now, let's see, that's actually 1%, what would it be? And I know power factor goes up with temperature, so I say, well, it's 1% at 35 C, but what would it be if I tested it again when it cooled off to 20 degrees C? But I don't know, I don't have this curve available to me to look it up and see what it would be. So I need to calculate what that is. And I've done this narrowband DFR measurement, so I have everything I need to figure this out. So basically, I plug the information into that Arrhenius equation, and I'm interested in knowing this value here. What's the power factor at 20 degrees C at 60 hertz? Well, when I figure out from my Arrhenius equation what that frequency shift factor is, then it tells me that, gosh, it tells me the frequency on my 35 degrees C curve, which corresponds to the 60 hertz frequency on my 20 degrees C equivalent. So when I plug these values in, I get a frequency shift factor of 0.177. And so basically that's telling me, hey, in order to get what I want, which is power factor at 60 hertz or at 20 degrees C temperature, that tells me that, okay, my power factor is 60 divided by 0.177 or 339 hertz on 35 degrees C. So I already measured the information I need by doing this narrowband DFR testing. It's telling me that, hey, you want to know what that 60 hertz is going to do if I let this cool off to 20 degrees C? Go up to 339 hertz on this green curve here, and that's going to correlate with the power factor at 20 degrees C, 60 hertz. So I can say, oh, that's such, and that's representative of my 60 hertz at 20 degrees C. And the beauty of this is the measurement is what is revealing the answer. So it's unique to whatever you're testing. So here's the curves from the dryer transformer. So again, it's basically 35 to 20, that same frequency shift factor. And I say, okay, I want to determine what my if I let my transformer cool from 35 to 20, and you can see that they're practically the same, it tells me, oh, well, again, you have to go to 339 hertz, and that will reveal your equivalent 60 degree hertz power factor at 20 degrees C. So the curves themselves are, going to, they tell you what that value is at 339 hertz. That's not a calculated value. That's yielded by the measurement. So this actually works in every single case. So the last topic, and I really apologize for going over, but this is just a few slides. I just want to mention about the predictive nature of testing. Can a test actually go from providing a condition assessment to actually providing prediction of future dielectric behavior? And this is kind of fun to explore. We don't have a lot of time to talk about it, but these kinds of value are added when you start looking at things like, for example, on the test voltage, the amplitude of it. On dry insulation that's prone and predisposed to partial discharge, one of the common tests that are performed are power factor tip-up tests or measurements. So you're performing the test at multiple voltages and seeing, well, what's my power factor doing? Is it changing or not? And that provides you a condition assessment of that insulation. But if you supplement that, and I'll show you a slide next, with a power factor test that goes just beyond the line to ground rating of the asset, if you're comfortable with doing that, then that gives you a predictive component, not just looking anymore at the condition of the insulation, but maybe what's to come in the future. And the same thing happens with the test voltage frequency. We're lucky that we have the luxury of since we're doing offline measurements in the controlled test environment, we're lucky that we have the ability to change all of these amplitudes and frequencies at will with our applied test voltage that set up these electrical fields around our insulation. But with the test voltage frequencies, if I do testing at several different frequencies around line frequency, that's going to get some unique condition assessment of the insulation. But if I broaden up my range, then it can become more predictive. And sorry, I just don't have time to talk about temperature, but I'll say with the voltage dependence, for an ideal oil paper insulation, what we expect is that power factor doesn't change with voltage. Okay, but then for a dry insulation, so you're dealing with like maybe dry type transformers or generators, motors, cables. This insulation, in this case, this would be representative of like a dry type transformer or cables. But as the voltage increases, it's not unexpected to see that the power factor increases. And what you then are vigilant about is how much does it increase, and that gives you, of course, a condition assessment. But if, as I explained before, if this is my line to ground point here, you see the vertical dotted line. Maybe I'll catch up with my mouse here. Here we go. If this is line to ground, and here's a typical response, a power factor with voltage for dry type insulation, the expectation is that with time, this curve will shift to the left, and that when I come back in the future to measure, then it's probably going to look like something like this. So if I can go out past line to ground and I can see what this power factor is over here, then I can say to myself, okay, am I going to be comfortable when I come back in a few years with my line to ground power factor being that high? Is that tip up acceptable? And also by going slightly above 2, it gives me an indication of whether all of a sudden my power factor really takes off once I get past that, and it's not a gradual curve anymore. And the same thing as narrowband DFR, right? So by going down, yeah, we can determine the slope of the power factor response to 60 hertz with just a few points around 60 hertz. But the value in going down to these lower frequencies is we are quickly doing an assessment, because the test doesn't take very long, to see, what kind of conductive losses may be at play, and to provide us with some kind of level of, gosh, you know what? In this case, any future, because power factor is the same for all 4 of these bushings at the line frequency, right in here. Okay, but how do I want to treat a trend happening in power factor going forward? Well, I'd probably be more apt to respond with great alarm if my X3 power factor at 60 hertz starts to trend high versus some of these others, given this extra kind of predictive information. And so the reason I bring this up is because if you start thinking about online monitoring, which is great, it's doing real-time trending of power factor and capacitance. So, and it gives you real-time notification of a change in one of those. But it's only going to be predictive as much as line frequency power factor is predictive. If all of this is happening, moisture contamination and other conductive or elements that contribute to conductive losses, if those are largely, not seen fast at line frequency, then online monitoring is only predictive as much as that's going to react to those kinds of changes. Whereas, the nice thing that is afforded by these offline measurements is it does give me the ability to get kind of more of a predictive feel of what's happening. And so we've come to the point in the presentation where we're ready to summarize the main messages, and I don't have too very many, but I thought that I would pull us all out of the rabbit hole that I buried us into and share a passage from a book I love called Oh, the Places You'll Go by none other than Dr. Seuss himself. Incidentally, this was his last published book, and in it he's offering some sage advice to a young adult setting off on his own. And I'm hoping you're reading this as I'm talking because I'm not going to read it to you, but it cautions him about staying too long in the waiting place. And it's actually perfect advice for people who are intuitively ready to take another step forward on their path, but and actually may not consciously realize that they've, in fact, been hanging out in a kind of a waiting place. So my first comment to summarize is stay out of the waiting place, right? You should perform power factor tests routinely. Continue to do that because it is an important tool for insulation health and for problems. But use an instrument that allows for narrowband DFR testing. The advantages are that it separates what seems like a good power factor, but it's really not representative of good insulation from, hey, this seems like a good power factor at the line frequency, and yes, in fact, it is a good power factor. So it separates those out. It provides better sensitivity to a lot of emerging problems, and importantly, it enables determination of that individual temperature correction. So always temperature correct your line frequency power factor values, but don't use those correction tables because they are going to introduce error, and there's already enough variables that we're contending with when we do insulation diagnostics, so you don't want to be adding an additional one. The suggested range for narrowband DFR testing is 1 to 500 hertz, because going down to those lower frequencies are really going to add to some, give you some good predictive value and come in handy for larger insulation systems as well, where you really need that ability to see conductive losses because you just can't see as well when you do power factor averaging tests on large assets. So finally, before I turn it back over to Jamie, I'd like to just say a few words about 3 mega test instruments that provide testing capabilities that we've been talking about today. So on the far left, our Delta 4000 is our dedicated capacitance and power factor test instrument, and it has narrowband DFR testing capabilities. Its frequency range is 1 to 500 hertz, and it includes the automatic individual temperature correction for you. It also has a voltage dependence detection feature, which I didn't talk about specifically during the presentation, but this is monitoring the harmonic content of the measured current, and it alerts the user when it believes that a voltage-dependent condition may exist in the asset being tested. And this would then trigger the user to perform a power factor tip-up test that you may otherwise not be planning to do. The track in the middle is our multifunctional solution for transformer testing, as well as providing circuit breaker testing capabilities and several common substation testing functionality. It's actually not just another multifunctional test instrument, though, but rather many intelligent instruments built into one box. And this distinction means it's important. It means that it's a lot simpler and more intuitive to use. And the software includes a number of apps that make it fast and easy to perform a large range of different tests. Many transformer tests can be performed, including power factor and narrowband DFR, and with the 1 to 500 hertz frequency range, and it includes all the functionality of the Delta with the ITC, the VDD, the voltage dependency detection, etc. And then lastly, to the far right, we have the IDAX, and this is Megger's DFR, full DFR test instrument. It will provide you analysis of the moisture content, the power factor, and the oil conductivity. And notably, it has some unique features that make it both extremely fast and at the same time highly reliable and repeatable in high interference environments. We just passed the over 20-year mark from when we introduced the first commercially available DFR test instrument. We're really proud to have made this technology accessible to so many people. Suffice it to say that Megger's got a lot of experience with this test, and of course you'll find the ITC capabilities with this instrument as well, and the ability to convert DFR results to a thermal response. Again, that's power factor versus temperature. So there's a survey at the end of the webinar. You'll find there a field for you to request a demo or quote for any Megger product if you are interested to learn more about these. But this concludes my presentation. I thank you all very much for your time and attention. And yeah, I wish you safety and success with your installation testing programs. And Jamie, sorry for the going so far over, but I'll pass it back to you now.
No problem, Jill. Thank you very much. All right, at this time, the presentation portion of the webinar is officially concluded. We will now take, or after a few messages, we'll take 30 minutes to answer as many questions as possible. So if you have any questions and you haven't already submitted them, you can go ahead and submit them now into the Q&A box on the right side of your screen, and we'll try to get as many of those answered as possible. For those that are leaving right now, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or quote on any Megger products. A copy of the presentation along with a link to the video recording of the webinar will be emailed to everyone within about 2 business days. Also, you can view video recordings of previous webinars on our website at us.megger.com/webinars and register for next month's webinar, which is titled Battery Impedance Test, Analysis and Trending. That'll be on September 21st at 10 a.m. Central Standard Time. And the presenter for that webinar will be Volny Naranjo, and he's our Megger Senior Application Engineer. And also, before we get started on the questions, I just want to make you aware of hands-on cable training courses from AVO Training Institute. They have a power quality and harmonics course, which is 4.5 days and offers 3.6 CEUs to attendees. You can visit avotraining.com to view their entire schedule of upcoming courses. And they've been training for over 50 years and have some very knowledgeable and experienced instructors. All right, now let's get to a few of your questions. The first question is going to be for Diego. Please state what the acronym DR or DFR means.
Well, good morning, everyone. When we go into the dielectric analysis, the terminology that we use is DR for dielectric response, and DFR is dielectric frequency response, or what we also call frequency domain spectroscopy. And it's basically the analysis of the power factor at different frequencies. That was explained very well today by Jill.
Thank you, Diego. Another question for Diego is, what standard lists 0.5% as the limit for power factor of mineral oil filled transformers?
That is a very interesting question, because on the standard, you will not see that it's the recommended limit. It's a suggested value to consideration. One of the most important things that you need to think about is not just on the limits published by standards. Power factor is more a historical data analysis. You should do some trending analysis on the power factor value. It's not just the 0.5%. It has to be complemented by the temperature value as well, right? It's not the same 0.5% at 20 degrees C trying to compare with a 0.5% at 10 degrees C. Jill, during the presentation, emphasized the importance and the effect of temperature on the dielectric analysis and all this dielectric testing. So you got to be careful on the 0.5%. 0.5% is a suggested value for analysis if you do not have a historical reference. Then this is the only thing that you can say, well, if it is over 0.5, I need to investigate. It's not saying any document that when you reach 0.5%, you need to scrap your transformer. So think about it. It's a suggested limit to start investigating and looking into more information if you do not have any historical values.
Okay. Thank you, Diego. Next question, another one for Diego. Can we do SFRA analysis on all types of transformers, or is it limited for some typical type of transformers?
One of the interesting things about this dielectric response, or I would say frequency response technique, because SFRA is not related to the dielectric directly, it's more related to the electromechanical condition of your transformer. But yes, SFRA, just think about it as a control process where you have an excitation signal or you have an input signal that goes through an RLC circuit, and this output is analyzed. You know, what are the changes of the input signal based on the circuit that is taking that signal from one end to the other. In this case, you're using just the winding. It doesn't matter if your transformer is a power transformer or a distribution transformer or a oil impregnated paper insulation or a dry type insulation. Actually, you can. I think that there's quite a few applications not only looking into the windings of transformers, there are applications looking into the windings of motors and generators. So I would say that the application of SFRA, the technology itself, has a wide spectrum of applications.
Thank you, Diego. Next question is for Jill. What do you mean by electrical insulation health?
Okay, that's a great question. Essentially, electrical insulation health is represents how well an insulation is supporting an electric field with minimal losses, and the condition in which an electrical or any suitable insulation material does that is, you know, when it's very dry, when it's clean, it's contaminant free, whatever the source of those contaminants may be, and I've seen so many that the material is relatively void free. And thinking about that, you know, how well was like the impregnation process when dry insulation was then impregnated with oil? Did all of the unavoidable voids you're going to get in a dry piece of insulation, were they all filled properly so that there's no localized stress anywhere in the insulation? So those kinds of characteristics. So by doing you know, power factor testing, narrowband DFR, full DFR, by doing various oil tests. These are all to increase our knowledge of insulation health and you know, how suitable are the materials to continue to do a good job of supporting an electric field and not, you know, well, worst case, dielectric failure is synonymous with failure of the asset, but even, you know, you don't want a lot of losses in that insulation system, because that's in turn going to advance its rate of deterioration and degradation towards a place where it's not going to do the job it was intended to anymore. So yeah, those types of things are what I mean by electrical insulation health.
All right, thank you, Jill. Okay, next question is for Diego. Can we use VFPF testing for cables?
Okay, let me put it this way. DFR, dielectric frequency response, the very first application actually was on XLPE cables, which is basically your medium voltage cable. It's a little bit of a different approach, the analysis, but there is a method for that. There's an analytical process that is being used using this variable frequency power factor analysis. So if somebody really is interested to know more about the application of DFR on cables, we can certainly give you some feedback and provide some information. So just send us an email later, and we'll be glad to support you.
All right. Next question, again, is for Diego. How is PF or DF analysis able to predict the life expectancy of a transformer? And then part two of that question is, what is the formula used to determine the minimum or maximum current loss, PF, DF, for a given transformer?
Okay. When we're talking about life expectancy, it's like looking into some crystal balls. I mean, you cannot predict 100% what the future will be or what the life expectancy will be of a transformer. What can you make a technical statement is on the condition of your transformer at the time of the test. During operation, many things can happen, and you can say, yes, this transformer is in good condition to work for another 10 years. Fine. Under what conditions? Assuming that you're going to run some maintenance programs, assuming that you're going to keep a load control, assuming that you will keep everything under thermal conditions according to the specifications of your transformer. There are so many things on this question talking about life expectancy that it might be in good conditions right now, and tomorrow you have a true fault shaking the windings internally on your transformer, damaging the insulation, and that'll be the end of it. There's different ways to approach the life expectancy question, right? There's ways to look into sometimes maybe furanic compounds. There's new methanol analysis. There's different things that could be somehow correlated to degree of polymerization of the insulation. And the only problem with the degree of polymerization on a direct testing mode is that you need to take a sample of the paper, and there's no significant sample of paper on your transformer that will give you that exact number of your degree of polymerization. So you can make an estimate. You can look maybe into some external factors like furanic compounds, but that's all it is. It all depends on what the operation is. And what we're trying to do with the diagnostic process is to make a strong statement on what is the health condition of the transformer at this point.
All right. Thank you, Diego. Next question is for Jill. What do the values of the axis indicate? And part two of that, overall two-winding transformer graph.
Okay, so I'm assuming that this question must have come in while I was going through one of these previous slides. So I'll try to back up to the assessment guidelines and find it here. So that's bushings. Here's the two-winding transformer. So on the y-axis, that would correlate to the power factor. Here we can see power factors at the lowest frequency and that was measured. The blue, for example, just over maybe 0.53%, 0.52% power factor. And then, of course, the x-axis is the frequency on a logarithmic scale. I'm glad the question was asked, so thank you, because I will make sure that I go back and I clean these slides up before they're made available to everybody, making sure, there's not other instances, which is completely possible knowing me, where I've left off that important information. So I appreciate the question.
All right, thanks, Jill. Next question is for Diego. I use the Delta 4000. Is it possible to perform tests at different frequencies and using the software to plot graphs?
The answer is yes.
Okay. Next question is for Diego as well. Temperature correction to 20C has played a significant role throughout the presentation, but lately standards are trending away from considering temperature correction. How does Megger plan to align themselves with the standard?
I think that we had a very interesting slide during the presentation looking at the statement from IEEE C57-1290. And what we need to understand is that insulation resistance or power factor testing is temperature dependent. When we understood this part, we understand also that the condition internally the condition of your transformer is different from one transformer to the other one. So you cannot be generic based just on the nameplate data, nameplate information that you gather from as a reference to estimate the correction factor for temperature. Megger, like it was described during this webinar, Megger has developed the individual temperature correction based on the fundamental principles based on Arrhenius equation, correlating the temperature change and the effect depending on the condition of the insulation system itself, based on the dielectric response that you get. So now that we have a unique dielectric response obtained from one specific transformer, we can estimate what is the thermal response of that specific transformer. So the approach that Megger has, the unique patent that we own, is ITC, the individual temperature correction, which looks into the condition of the insulation, which looks into the specific dielectric response of that insulation system, and based on that, we derive what will be the thermal dependence or the thermal characteristic of that insulation system.
All right. Thank you, Diego. Next question is for Jill. Any different considerations on NB DFR testing dry type transformers?
Wow, that's a great question. And a challenging question to answer, right? So, dry type transformers are, they're a completely different animal when it comes to testing, and the industry's really struggled with those, even with, I mean, never mind the narrowband DFR testing, but even in line frequency power factor testing. So I'd say the answer to this question is yes, there definitely should be different guidelines. I could imagine with the general, just because of their construction rather, and losses being, characteristically maybe more conductive losses at play. I would be, and I'm going on a limb because as you'll probably hear me talk through this, we don't have a lot of data yet for narrowband DFR. I have some, but I would not raise a flag for alarm if my slope through my line frequency power factor wasn't positive. If it was negative, I don't think I would be surprised, because of the dry type transformer, it being prone to more kind of conductive loss. And on the flip side of that, it's interesting because I'd also be, I think dry type specimens are just so interesting, and but on the higher frequency range, up towards the 500 hertz, I'd be, we test dry type transformers, or suggest to, at different test voltages, because the materials, since they're never impregnated with oil, they are prone to partial discharges. So, in that kind of instance, I would think that, maybe the tails of the narrowband DFR plots might look a little bit different as well. We might have to give more allowance for, those tails to be a little bit higher, but it's all very interested. And to the person who posed the question, if you have access to a lot of dry type transformers and have an interest in this, Megger would be really interested in partnering with you to get some more narrowband DFR data and further our understanding of insulation diagnostics on these dry type transformers. They're kind of the stepchild and been left out quite a bit, but there's so many of these units out there. So I definitely advocate towards furthering our understanding. But absolutely, yes, I don't think that the guidelines I gave would be something I would expect to happen with a dry type unit.
Okay, thank you, Jill. Next question is for Diego. This webinar has focused on testing of insulation for transformers. Is it also capable of evaluating MV cable insulation, for example, EPR, etc.?
As I mentioned before, and we already had a question related to cables. One thing that you have to remember again is that dielectric diagnostics could be on any type of insulation material, right? And the application of DFR or dielectric frequency response can be applied to many different types of materials. I would strongly suggest that if you are more into the medium voltage cable, I would strongly suggest to look into the webinar that we presented for cable diagnostics, and you will see the different techniques that are applied right now and are available in the market to do cable diagnostics. You will go into tan delta applications, partial discharge. You will see the VLF application. So there's different techniques for diagnostics, and there's other techniques applied for cable fault location. So I do invite the person who asked this question to go into our website and look into the webinars that were presented on cable diagnostics. Or just email us and we'll be more than glad to assist you with further questions.
Okay, thanks, Diego. I have another question for you. Are there any further studies for distribution transformers using GFRA since there is less slide insulation materials, wood, pressboard, than the large power transformers?
This is a very interesting question, and I should say that Megger has been working on this technology for the last 20 years at least. When we look into different types of transformers, we are not looking only into the large type transformers. Nowadays, the application of DFR has expanded on our capabilities and the knowledge that we have incorporated into our systems for high voltage bushings, for high voltage current transformers, different type of instrument transformers, and also the small distribution transformers. I understand the question that you have because there's complexities on the different construction of sometimes smaller distribution transformers, but we have the information and we know exactly how to deal with the smaller distribution transformers. So yes, maybe on the next webinar we will focus more on the smaller units, on distribution transformers, on bushings and CTs, to give you additional information on how do we approach this question.
Okay, thanks, Diego. All right, looks like we have time for one more question. Last question is going to be for Jill. Is the individual temperature correction for the unit under test or for the test instrument?
Okay, so the answer to that straightforward is that it is for the unit under test. And the whole reason behind this is, like Diego said, we know that power factor varies depending on the temperature, and that, you know, if we were to go out and say, I have in hand a power factor result from 3 years ago, and the unit was tested at 18 degrees C top oil temperature, and I'm out there today, and this is kind of really important. I've been triggered to do the testing by some kind of alert, and so the transformer just comes offline, and I'm right in there testing it, so maybe the top oil temperature is like 45 degrees C when I'm doing my test. Well, the expectation is that just because of the temperature alone, that I'm going to be measuring a higher temperature. And so say, in fact, I do measure a higher power factor, or a higher power factor, sorry. So say, in fact, I do measure this higher power factor, and it's at, say my power factor now, before it's 0.3%, and now it's 0.68%. Well, my question is, okay, well, is that variation? I see I have a variation. Should I be alarmed or not? Is it all due to temperature? Or is it, if I corrected it back to what it would be if I waited around until the transformer cooled to the top load temperature of 20 degrees C, you know, would it go down to 0.3 or not? And so the temperature correction, which can only be done on a case-by-case, it would depend on what the transformer is, how aged it is, you know, what its condition is. But the whole point in figuring out that individual temperature correction for that transformer would be to know exactly what the power factor would be if I waited for it to cool down to 20 degrees C without waiting actually for it to cool down to 20 degrees C. And that way, if I, you know, determine that, gosh, you know, the power factor is in fact still not 0.3%, it's, you know, it's 0.5%, then I can say, oh gosh, you know, that's a pretty significant change from previous. So there's definitely some more testing in order here to get to the bottom of why that change has happened. So, yeah, the short answer is no for shorts for the transformer under test.
And I would like to add to Jill's comment that it is very important not only to look at the narrowband dielectric response, which was the focus of this webinar, but remember the importance of the frequency ranges that we have been looking at. We do the frequency narrowband analysis between 1 Hz and 505 Hz, which allows us to look into details that are related to this transitional effect going from the liquid insulation to the solid insulation, and allows us to do this individual temperature correction that is unique on the system. But again, the frequency band that you require for this is between 1 Hz and 500 Hz.
Okay, do you have anything else on that, Jill? Or?
Yes, I would like to thank everyone who has stayed around this long. I know we've gone over, but these have been great questions today, and I really enjoyed myself and this opportunity to discuss the narrowband DFR testing with you.
Okay, thank you, Jill, and thank you everyone for attending. Please remember to fill out the survey if you can. We greatly appreciate it. And I just want to thank you all again, and have a great weekend, everybody.